In the previous video, we talked about how to do some basic manipulations on matrices, how to create those matrices, how to work on the diagonals, and how to actually do some simple calculations using those matrices, right? And the purpose for doing this kind of thing, one of the motivating problems we are trying to actually solve is this algebra problem, right? At the beginning of the previous video, we described what the problem actually is about, right? So Joe counts 48 heads and 134 legs among chickens and dogs on his farm. And how many dogs and how many chickens does he have, right? It's an algebra problem. So the two equations that we come up with is d plus c equals to 48, right? So d plus c. So d is the number of dogs, c is the number of chicken, right? So each dog has one head and each chicken has one head. So the total number of heads add up is 48, right? That's the first equation we had. And then 134 legs, right? Each chicken has 2 legs, and then each dog has 4 legs. So 4 times the number of dogs, that's d, plus 2 times the number of chickens, that's c, equals to 134. So we basically have these two equations, right? And then we need to solve for d and c, right? And if we just solve this equation by hand, it's not too hard to solve, right? So you just divide 2 on both sides of this equation. So it's 2d plus c equals to 67, right? And then you can just subtract these two equations. C and C cancels out. 2d subtract d, that's d, right? 67 subtract 48, that's 19. So d equals to 19, right? And then you can bring d back into this equation and solve for c. C equals to 29. So for this very simple algebra problem, the solution is relatively straightforward. You can just solve it by hand. It's not too difficult. But the goal, our purpose, is to actually come up with a more general algorithm that allows us to solve this kind of linear systems, a system of these kind of linear equations, in a more systematic way, right? And our approach should be applicable to not just the two variables, right? Our code should be applicable to any number of variables and any number of equations, right? Suppose we have like a 100 or 200 or 1 million variables, 1 million equations. Our code should, or our algorithm in general, should be able to actually solve those problems without any kind of modification to the code. So how do we actually sort of cast this kind of problem into a more general form, right? So if we look at these two equations, the d and c is basically the unknown variables. The number of dogs and the number of chickens are the unknown variables, right? And then we have some coefficients that's multiplying those unknown variables. So for the first equation, the coefficients multiplying in front of those d and c is unity, 1, right? So it's 1 times d plus 1 times c. And in the second equation, the coefficients that's written in front of those unknown variables is 4 and 2, right? So let's put those coefficients inside of a matrix, right? So for the first equation, it's 1 and 1. So the first row has 1 and 1. And then the second equation has 4 and 2, right? So in the second row, we have two columns, 4 and 2. Right? And then this matrix, that's a matrix that's we have specific numbers in it, right? And then we use this matrix to multiply with a vector, a column vector with 2 rows in it, right? And d and c. For now, we don't really know what's actually the value for d and c, but let's just use the symbol d and c to represent the two values in this particular column vector, right? And then on the right-hand side, we have two numbers, 48 and 134, right? And then let's just construct another column vector with 2 rows, and 48 on top, 134 on the bottom, right? So these two, what I claim is that these two equations is actually equivalent to this particular linear system. something that we call a linear system. It's basically the same thing, right? If you don't believe me, you can try to actually carry out this matrix vector multiplication in your head, right? So how do we actually do matrix vector multiplication, right? So this row, the first row, do a component-wise element-wise multiplication with the column, right? So it's 1 times D, and then plus 1 times C, right? So that gives you the left-hand side of the first equation, and then equals to 48, the first element in the right-hand side. That's 48, right? And then if you do matrix vector multiplication on the second row, this column, that's 4 times D, right? Plus 2 times C, and then equals to 134, right? So if we write these two equations in this particular form and use the rule of matrix vector multiplications, we can actually recover these two equations, right? So these two equations is equivalent to writing is equivalent to this particular representation using matrix vector operations, right? So now we have come up with sort of a slightly more general form to represent these two equations, right? But now let's introduce more symbols. Let's introduce more symbols. We have this particular matrix. Let's just use capital A to represent this particular matrix, right? And then let's just we have this column vector. Let's use the symbol x, small x, to represent this column vector. And then we have this column vector. Let's use small y to represent this column vector, right? And then this particular equation, this matrix vector multiplication form of the two equations here, can now be represented as A, this matrix, multiply with x, this vector, and then equals to y, this another vector, right? So now the problem becomes, how do we actually solve for x, right? Because this x vector has the two unknown variables in it, D and C, the number of dogs and the number of chickens, right? That's the thing that we want to solve, right? That's the numbers that we want to solve. For now, we don't really know what's actually inside of D or C, right? So we need to solve for x. So how do we actually solve for x, right? How do we actually solve for x? The idea is that if we can come up with a matrix, another matrix, we denote it as A with exponent -1. But it's just another matrix. It doesn't really matter how you actually represent it. You can call it B, or call it C, or call it whatever name you want to use, right? Here we are just using A with the exponent -1, right? Suppose you can come up with this particular matrix, right? And what this matrix, if you multiply this matrix with the matrix A, if you do matrix multiplication between A -1 and A, and if you get a identity matrix I, right? If this thing multiplied with this matrix A equals to an identity matrix, then we call A -1 is the inverse of A. And because A -1 is multiplied with A on the left side, so it's essentially something that's called a left inverse, right? So you can imagine there might be a right inverse, right? So if you multiply this particular matrix on the right hand side of A, and you still get an identity matrix, then it's also a right inverse, right? So it depends upon which direction, on which side you multiply with A with, and if you get an identity matrix, then it's a left inverse or right inverse. And usually, in practice, it could be different. The left inverse and the right inverse could be two different matrices. It doesn't have to be the same, right? So why do we want to get to an identity matrix, right? Why do we want to get an identity matrix? So if you have this A -1, this inverse matrix, and then you multiply on both sides of the equation, so A -1 times A gives you I, right? So I times X, right? Don't forget, what exactly is I times X? So in the previous video, we did some examples about the identity matrix. If you multiply identity matrix with any kind of vector, you get the same vector back, right? So identity matrix multiply X equals to X, right? And then on the right hand side, you have a minus 1, that's the inverse, multiply y, right? So a minus 1 multiply y, right? So if you can actually come up with the inverse a minus 1, you multiply with the right hand side, this vector y. We know y, right? The numbers inside of the y vector is given 48, 134, right? So if we can come up with a minus 1 times y, then we have solved the equation, right? We got an explicit representation of x, right? And then the trick, the difficulty is just how do we actually come up with the inverse, right? How do we actually come up with the inverse? How do we actually construct the inverse, right? So what I'm gonna do is that I will go to MATLAB and try to construct the inverse using a iterative approach. That's called the steepest descent method, right? It's an iterative method. The idea is that I assume a certain x. I start with some kind of assumption about x, say 0, 0, right? X has 2 zeros in it, right? Of course, this assumption is most likely it's different from the actual solution, right? But it's okay. It's okay. I do this matrix vector multiplication with A because A is given, right? And now I have assumed the values inside of x. I do matrix vector multiplication, right? And then of course, the result of this matrix vector multiplication, that's the left-hand side, it's going to be a vector, right? It's going to be a vector. And that vector is going to be different from y, right? The reason is because x is not the correct solution, right? It's some value that I just assumed arbitrarily, right? So the left-hand side will not be equal to the right-hand side, right? But it's okay. I can compute the difference. I can just use the right-hand side of the actual y to subtract this a times x, this matrix vector multiplication result, right? And this kind of difference actually tells me how I should actually modify my guessed value, my assumed value in x. And then I make a correction to the x using that difference, basically, using some kind of transformation of that difference, right? And then I after this correction, I may have a better estimate of the x, right, which might be closer to the actual value, right? And then I do this matrix vector multiplication again using this kind of corrected value of x, right? And at this stage, the correction could work, could not work, right? There might be still differences, right? And then I do the same thing again. I subtract the actual y with the calculated y on the left-hand side, right? And then it's going to give me another difference. I make another correction. So if I repeat this kind of step many times, eventually I can come up with the correct x. The correct x. Right? So that's the basic idea. The trick is just to understand how do we actually make the correction. What's supposed to be the correction, right? What's supposed to be the correction? So how do we actually modify x throughout the iterations? So now let's get back to MATLAB and look at how we can actually solve this particular problem, right? So we're gonna start with a script, and later on we're gonna convert it into a function, right? So let me write a comment. Solve the following problem using steepest descent, right? And then the first thing I'm gonna do is to actually construct the matrices that I'm gonna need, right? So A matrix, its first row is 1 1, right? Let me take a look. The second row is 4 2, and then semicolon 4. And then Y matrix, or Y vector. Y vector is 48 134. Right? Y vector 48 134. That's my Y vector. Right, and what I'm going to do is that even though I have, let me save the code first. Right, let's just call a matrix INV or inverse. Right. So even though I don't really know what's actually the correct value inside of the x vector, but let me assume a value. Let's just assume the value is 0 0. Right, x equals to 0, 0. So x, it's a column vector, right? So with two numbers, let's just assume that x actually has value of x 0, 0 inside of it, right? 0 dogs and 0 chickens. So now let's try to actually solve this problem with this particular iterative approach, right? Every time we solve a certain problem using the iterative approach, we can think of a loop, right? Every time we talk about iterative things, we are thinking about loops, right? So for now, the only sort of loop that we know about is the for loop, right? Later on, we're going to talk about different kinds of loops, while loop, which is actually extremely useful, especially for this kind of problem. But for now, let's just use the for loop. So if we are using a for loop, we need an iterator. Let's let's call it I. It goes from, say, 1 to the total number of iterations. What's going to be the total number of iterations, right? We could put like 10,000 here, right? Or whatever big number that you want to use, right? But let's not use a specific number. We talked about the abstractions, right? We talked about abstractions before. It's not a good idea to use a specific number. Let's abstract it away by using a symbol. Let's call it ni, number of iterations. Ni. Let's give it like 10,000. Right. So later on, when we actually try to encapsulate a certain section of code into a function, we can just sort of use ni as one of the inputs or something to that function, and so that's gonna be the loop that we'll try to actually construct. Right. So the first step is what I was just sort of talking about. The first step is to use this A times X to do a matrix vector multiplication. Right. Let's just write the code for that, and we have our own function for doing matrix vector matrix multiplications, which is called matlab12, right? Do I have this thing in my work? It's not in my, but it's okay. Let me grab that function. matlab12. Let's hear. Right. We can use MATLAB's internal operator, multiplication operator, right? But let's still use our own function, right? Because this problem is not too big, so efficiency is not really a huge concern. So so let's still use our own function, because we wrote this function, so we know better about this function. So if there's anything wrong about it, it's going to be easier for us to actually correct it. So let me just quickly actually copy over that particular function. Why it's not allowing me to copy? Very strange. It's not allowing me to copy. Did I actually do a copy right? Control C, Control V, right? Control C, Control V. Yeah, now it looks like this will work. Let's save it. Okay, so the first thing we're gonna do is to do matlab12. Don't forget the ordering. The ordering is actually kind of important, right? Which one actually goes in at the first input and which one actually goes in at the second input, right? So we're actually computing what? We're computing A times X, right? We're not computing X times A, right? If we are doing X times A, then the matrix dimension is not going to match. So the first thing that we put into the multiplication is A, right? That's the first input. And then X is the second input, right? And then we need to actually store the output. So the output is going to be different from the actual Y value, right? The actual Y value is 48,134, But you can imagine if you are just using some kind of assumed x value to do the multiplication, right, 0, 0, then it's gonna be different, right? So let's call it y pred underscore pred. So the matrix vector multiplication results from the matrix vector multiplication are gonna be stored in this particular variable. So here we are using an underscore inside the variable name, and that's allowed. That's allowed, right? So y underscore pred. So basically, you can use underscore to actually separate the different words in a longer variable name, that kind of thing. So now we got the predicted y, right? By using this assumed x, right? This wrong x basically. So now we need to actually come up with a vector that quantifies the difference between this predicted y and the actual y, right? That's called error, or ERR. Let's just use a shorthand ERR to save some typing. You can use error, but it doesn't actually, because but it's probably gonna be a, because error is actually a MATLAB intrinsic function, right? So it's not a good idea to actually reuse MATLAB's intrinsic function as a variable name. It's not a good idea. So we can just use ER to represent error, and that's gonna be pred subtract y. So in MATLAB, this subtraction, just like addition, so by default it's gonna do a component-wise subtraction. So what it's gonna do is that it's gonna actually use the first element of y underscore pred to subtract the first element of y, and then use the second element of y pred to subtract the second element of y. And then the results of these two subtractions are going to go into ERR vector. So ERR is going to be a vector with two elements, right? The first element is going to be the difference between the first elements of y pred and y, and then the second element is going to be the difference between the second elements of y pred and y, right? So that's the difference. That's sort of the difference, right? That's sort of the difference. So now let's try to make the correction using this particular difference, right? Make a correction to x. So how do you actually make a correction, right? So now let's introduce another vector. Let's call it g. Later on you'll understand why I'm naming it g. It's something that's called a gradient. So g equals to what? G is going to be computed from this error vector, right? But it's another matrix vector multiplication. So this error is going to be vector, right? And then the matrix I'm going to multiply with this error is going to be the transpose of A, right? So I call my math_mal again. But this time, the first input that goes into the function call is going to be the transpose of A. And in the previous video, we talked about how to actually get the transpose, right? Just to use use a single quote. And then the second input, that's the vector, which is the error vector, right? So if I do this A transpose times error, this kind of multiplication, then it's going to give me another vector. So A transpose is 2 by 2, right? 2 by 2. ERR is 2 by 1, right? So the output is going to be 2 by 1. So G is going to be a 2 by 1 vector, right? And then at this point, I can use this G vector to correct my X, right? So how do I actually do the correction? X is going to equal to X subtract G times a constant. And this constant is something that we can adjust, which is going to change the behavior of our algorithm. Let's call it AOR. So AOR, let's 0.1. Right. Let's just is that a good value? Maybe too big, but anyway, let's just, so it's a constant value, right? But it's something that we can adjust. So in the literature of machine learning, it's called learning rate, right? So that's why we're calling it AOR, AO learning R learning rate. In the literature of machine learning, it's called learning rate, right? It's some number that we can adjust later on to change the behavior of our code, right? And then we can just use this AOR, this constant, the learning rate, multiply with this vector, right? So it's gonna do a component-wise multiplication with this particular scalar, this number, right? And then x is gonna subtract this number, and then the result of this element-wise subtraction is gonna be assigned back to x, right? So after one iteration, it's gonna make one correction, and then after two iterations, it's gonna make correction twice, right? And every time the correction is gonna be recomputed based upon this error, and this error is gonna be different because x actually changes from iteration to iteration, right? The only thing that doesn't change is a, right? A is kind of fixed, right? And it's not changed throughout the iterations. A prime is not changed either, right? The transpose is not changed either. But everything else keeps changing from iteration to iteration. So x keeps changing here. This line actually changes x from iteration to iteration, right? And then AOR is not changed, right? But it's a constant. But g actually keeps changing because g equals to a prime times error, right? A prime doesn't change, but error changes, right? Error equals to y underscore pred subtract y, right? And y underscore pred was computed from a, right? And then let's just run this code and see if it's gonna work. So it looks like it's actually getting close, right? We started with 0, 0. The correct value is supposed to be 1929, I think, right? It's getting close, but it's not there yet. Maybe I should just change the learning rate to a smaller number, to a larger number, so that it can converge faster. Let me run it again. Right, 1929, right? And in fact, it doesn't really matter what the starting value actually is. Let me give like 150, 150. It's always going to converge to the correct value. Right, 1929. Right. It's always going to converge. So that's sort of the code, right? That's sort of the code. But why? But why this code actually works, right? Why this code actually works? What's actually the reason behind it? Right. To fully understand the reason behind it, we need to understand this particular line actually, right? Because this is actually the critical line that allows us to actually make a sensible correction to x, right? But in order to understand this particular line, it's going to take some understanding about the linear algebra, right? If you have no background in linear algebra, it's actually going to take a while to actually explain through it. You need to understand what's actually something that's called a gradient. A gradient is what? Gradient is basically a derivative. It's basically just a derivative, actually. So it's the vector g that we are computing is actually the derivative of something that we call the objective function with respect to the two elements inside of the x, right? So you compute the gradient by doing this kind of a transpose multiplied with the error vector, right? And derivative is telling you what? Derivative is actually basically telling you how you should actually change the independent variable x so that your objective function becomes smaller, right? So that's something that's gonna take a while to actually explain. But let's try to understand how the code actually behaves in a graphical way, right? Let's try to understand how x is actually changing throughout the iterations. We started with some value, arbitrary value, 150, 150. And then we ended up with the correct value. But how x actually keeps changing throughout the iterations, right? And by looking at how x actually changes, we may gain some insight about the behavior of this particular, the so-called steepest descent area, right? So how do we actually come up with some kind of visualization of the entire process, right? Visualization. Visualization of steepest descent process. And here it's our chance to actually look at some more sophisticated MATLAB plotting functions. Right? We looked at some of the basic functions like plot, right? But this time we're going to look at how do we actually visualize two-dimensional things, two-dimensional graphs. How can we actually do that, right? So what's going to be the thing that we're going to try to visualize, right? So basically we have two unknown variables, the number of dogs and the number of chickens, right? That's just the two unknown variables. And then we're doing this kind of a calculation, right? We're doing this kind of calculation. So we're assuming some number of dogs and some number of chickens, and then we do this matrix vector multiplication, right? We do this matrix vector multiplication, and then we do this subtraction, right? That's the predicted y value and the actual y value, and then we come up with an error vector, right? So let's try to actually visualize how the length of this error vector varies with the assumed number of dogs and the assumed number of chickens, right? How can we actually come up with a visualization of that, right? So suppose we have like two axes. The horizontal axis is the number of dogs, and the vertical axis is the number of chickens, right? And then for every point on this two-dimensional plane, it's actually one assumed value, one assumed x, basically, one assumed x, right? Because every point on this plane is going to have an x coordinate and also a y coordinate, right? The x coordinate basically tells you the number of dogs, and the y coordinate basically tells you the number of chickens, right? So how can we actually come up with a visualization of the length of the error vector for every point on this two-dimensional plane, right? We're going to use colored contours. We can use colored contours to look at how this length of the error vector, actually varies throughout the entire two-dimensional plane with the two axes given by the dogs and the number of dogs and the number of chickens. So next thing we're going to do is to write a function that allows us to actually compute this length of the error vector. Let's try to write a new function, right? And the input arguments are going to be all the things that we're going to need in order to actually compute the length of the error vector. So what's going to be the things that we're going to need in order to compute? We need the A matrix, right? We need the actual y, right? And then the last thing we need is the assumed x values, right? That's basically the points that's on the two-dimensional plane, right? So we're going to need A, that's the matrix. We're going to need the y, that's the vector, the actual y vector, right? And then we're going to need an x, right? Let's call this function my ER-L2, right? What exactly does L2 actually mean, right? L2 is a way for you to actually measure the length of a vector. Later on, you're going to see how I actually compute the length of the error vector, right? And the output, let's just call it ER L2, right? That's going to be our output. So A is a 2x2 matrix, right? At least for our example that we're thinking right now, right? But later on we could actually generalize it to matrices of any kind of dimension. Y is a 2x1 vector, right? So in principle, X is supposed to be 2x1, right? X is supposed to be 2x1 vector, right? But let's assume that we have not just the one point that's sending into the function as input. We have multiple points on that two-dimensional plane, right? Suppose we are trying to actually construct a mesh on that dog-chicken two-dimensional plane, and then every point on that mesh has these two coordinates, right? Suppose we actually concatenate the coordinates for every mesh point into a sort of longer thing, right? Longer matrix, right? So the first column is going to be the dog-chicken coordinates of the first mesh point, and then the second column is the dog-chicken coordinate for the second mesh point, right? If we do that kind of thing, then what's actually coming into X is going to be a two-row matrix with a certain number of columns, right? We don't really know. It could be like 100 columns if we have 100 grid points, right? It could have like 1 million rows columns if we have like 1 million mesh points, depending upon how we want to sample, how dense we want to sample the dog chicken two-dimensional plane, basically, right? So the column number of X is going to be, we cannot fix it. We have to sort of compute it from the input. Let's call it NC. It's going to equal to the size of X, right? So wiggle means that I don't want this particular output, right? So size is going to return two outputs, the number of rows and the number of columns, right? But I'm not going to use the number of rows. I'm just going to use the number of columns, right? And then we can just loop through all the different columns inside of X and then do this calculation, A multiply X matrix vector multiplication, right? And then compute the Y pred and then compute the error, right? So for IC goes from 1 to NC, and then Y pred is going to equal to A times, I'm going to use my math actually, A times X, but it's arbitrary row IC column. So this colon actually means we looked at how to use the colon operator before when we actually were trying to actually deal with the vectors and matrices, how to extract those elements outside vectors and matrices before, right? But when we used the colon operator before, we always had something in front and something behind. And the something in front and something behind is the starting value, the starting index, and the ending index, right? But here we are not exactly specifying the starting index and the ending index, right? So if that's the case, MATLAB is going to assume that the starting index is going to be 1, and the ending index is going to be the keyword end, which basically represents the last element of that particular range, right? So for the column index, for the row index, so for the row index, we are not specifying the starting value and the ending value, right? Which means it's going to take all the rows. But for the column index, I'm specifying IC actually. So for the first iteration, IC is going to be equal to 1, right? So this syntax is going to give me the first column, right? First column, all the rows on the first column. And then for the second iteration, this syntax is going to give me all the rows on the second column, right? So that's going to be this is a 2x2 matrix. But if I take this syntax for every iteration, the thing that's actually computed here in this code is going to be a 2-row, 1-column vector, right? So the dimension is going to match, right? And later on, once we so why do we want to do this kind of iteration, right? We don't really have to do this kind of iteration over columns. What we can do is basically just we don't really have to do this particular iteration over columns, but writing it like this kind of way, it's probably easier to understand, right? But right. So that's gonna give us a Y pred, right? That's right. That's the Y pred, and then we can compute the error, right? Error equals to what? Error equals to Y pred subtract Y, the actual Y, right? And then we need to actually get the length, get the length of the error vector, right? Get the length of the error vector. So how do we actually get the length of the error vector? Error is a 2-number vector, right? So what we are going to do is that we're going to square each element inside of the error, this ER vector, right? We're going to do an element-wise square. So ER dot hat 2. So what does this dot actually mean, right? And how does this thing different from just a hat? right? So dot hat 2 means that I want to square every element inside of ER. So the result of this calculation is still going to be a vector. But the output vector, every element inside of the output vector is going to be the square of every element inside of the ER vector, right? But if you remove this dot, then MATLAB is not going to treat it as a element-wise square. What it's going to do is that it's going to replace this hat 2 with a linear algebra multiplication. It's going to do this kind of thing. And this star is going to be linear algebra multiplication. So ER is going to be 2 by 1, right? It's going to do a linear algebra multiplication with another ER. That's again 2 by 1. Right? But if you do linear algebra multiplication, then the dimension is not going to match. So it's actually going to give you an error message. Right? So if we want to actually do a element-wise power, you have to use a dot followed by a head, by pointing the head, and then followed by the power. Right? And then the result of this calculation is going to be a vector. Right? And then what I want to do is to actually sum over all the elements inside of that vector, right? That's a summation of all the elements. So the result of this summation is going to be a scalar. It's just a single number. And now I can actually take the square root of the summation. And now my calculation is like complete, right? But the thing is that I need to actually store the result of the calculation into a something that can be used as the output. The output here is actually error L2, right? So let's try to construct a vector. Let's call it zeros, and then what's going to be the dimension, right? What's going to be the dimension of it? We're going to use one row but NC columns as a dimension, and then here I'm going to just assign ER L2. Assign the result of the calculation to the IC's element, right? To IC's element. And by now my function is done, basically. My function is done. Let me save it. Right. So now I can actually use this function to actually compute this this error on a mesh, on a two-dimensional mesh over my dog chicken plane, right? So how do I actually generate the mesh? How do I actually generate the mesh, right? How do I actually generate the mesh? There's a special method function called MeshSquare. It's a function that allows us to actually create a two-dimensional mesh by using one-dimensional coordinates, right? So suppose if you haven't used the MeshSquare before, help MeshSquare is going to tell you how to actually use this particular function, right? You can sort of see that here it's actually specifying a range for the horizontal axis with an interval of 0.2. So you're going to sample the horizontal axis from -2 to 2 with an interval of 0.2. And here you're going to sample the vertical axis from -4 to 4 with an interval of 0.4. Right? And then MeshSquare is going to take these two inputs and then create a two-dimensional mesh that's called capital X and capital Y. Did you see how MeshSquare actually works? So capital X is going to store the X coordinates for every point of that two-dimensional mesh. And then capital Y is going to store the Y coordinates for every point of that two-dimensional mesh, right? So let's try to imitate this particular usage, right? So suppose the number of dogs goes from say -100 to +200, right? With an interval of 1. And then the number of chickens goes from -100 to +200. Also, right? And then let's just store the output into dog chicken. We're using capital D, capital C here, right? So we're sampling the dog axis from -100 to +200, and then we're sampling the chicken axis from -100 to +200. Both of the sampling are actually sort of with a stride of 1, and then the capital D is gonna store the total number of dogs. It's gonna store the number of dogs for every mesh point of this two-dimensional mesh, and then C is gonna store the number of chickens, right? For every grid point on this two-dimensional mesh, right? But if you run this piece of code, let's hold down the control key and press enter, then it's gonna run this piece of code. If you take a look at what's actually the size of D and C, both of them are actually matrices. So 301, 301, right? Size of C, 301 and 301, right? So these two are matrices. They are not vectors, right? But our function myER_L2 actually takes an X that's 2 rows, right? That's 2 rows. So how do we actually convert the D and the C into a format that can be actually put into as the last input to myER_L2, right? So if we do this thing, again with no starting and ending index of the colon operation, then MATLAB is going to convert this matrix into a vector. It's going to convert it into a column vector, right? But if we transpose it, then it's going to become a row vector, right? And then that's going to be the horizontal axis, the number of dogs, the dog axis for every mesh point that's flattened out into like a 1 row, right? And then we need a second row, which is actually the number of chickens. We do the same thing, right? And then we concatenate these 2 row vectors into one matrix that's called capital X, right? So capital X is going to be a matrix with 2 rows and how many columns? It's 301 times 301, right? That's this many columns, right? Maybe it's a mesh that's probably too big. Let's change it, right? Let's go from like -50 because it's very unlikely to have negative numbers of a chicken thing, right? Let's change the dimension. Yeah, let's rerun it, right? So now let's look at the size of X. That's 2 rows, this many columns. Why this many columns? That's 251. 251 times 251. 251. Right. That's exactly the same, right? And now we can call our myER_L2 function, right? So the output is going to be, let's call it ER_L2. myER_L2. And then A is the first input, right? A is the first input, and then the second input is supposed to be Y, right? The actual Y. And then the last input is going to be our X that we just constructed, right? And then let's again run this code, right? And then let's check the dimension of ER_L2. It's 1 by this many columns, right? That's the ER_L2 that's computed for every mesh point, every grid point on our two-dimensional mesh, on the dog cat plane, dog chicken plane, right? But in order to actually visualize it, we still have to sort of convert this 1 row, this many column vector, into a two-dimensional matrix that has the same dimension as D and C, right? We need to actually map this one-dimensional vector into a two-dimensional mesh. Then we can visualize it, right? So now let's change the dimension of it. So how are we going to change the dimension of it? Let's call it. So now let's come up with another variable name, ER_L2 2D. 2D is going to equal to, we're going to use another MATLAB function called Reshape. So again, we can type help Reshape to look at how to use the Reshape function. So that's X, right? That's the matrix or vector that you try to actually change its shape. You're going to use all the elements inside of the X, but you are just going to reorganize all the elements into some kind of dimension, right? M rows, n columns, or you can do this thing: m rows and n columns inside of a vector, right? So we're going to change the dimension of ER-L2, and then what's the dimension that we want to use, right? We want to use the dimension of either D or C. Doesn't really matter. You could change to C here. Doesn't really matter, right? It doesn't. Either case actually works fine because D and C actually has the same dimension, right? And so now we are done. We're done with the calculation that's needed for the visualization, right? And how do we actually visualize it, right? How do we actually visualize it? So first thing we're gonna do is that we're gonna open a figure, and then we're gonna before we hold on, let's open figure 1. Right? And then we're gonna use a special MATLAB function called contour. Contour, F. Contour is one word, right? What's actually the meaning of F, right? F means fill. So the contour lines are gonna be filled up with colors between neighboring contour lines, basically, right? And then it's gonna take at least 3 inputs. The first input is going to be the horizontal axis, the mesh points, the x coordinates of all the mesh points, basically. And then the second input is supposed to be the y coordinates of all the mesh points, or all the grid points. And then the last input is going to be the value that you want to sort of visualize, which is ERR L2 underscore 2D, right? And then what's going to be the last input, right? The last input is how many contour lines do we want to see on the graph. Let's say 50. We want to see like 50 contour lines, right? And that's sort of the syntax for MATLAB to actually plot contour lines, right? And then we're gonna sort of decorate the figure a little bit. We're just gonna make sure that the axis for the horizontal and vertical axis are gonna be maybe that's the next step. Let's first make the plot first and see what's actually gonna happen. Is it done calculating? Okay, so that's my figure. Maybe 50 contour lines is like too many. Right. So usually those hot colors, warm colors means high values. Those cool colors means low values, right? So you can sort of see the length of the error vector is the smallest in this kind of contour, within this particular contour, right? But this kind of visualization is kind of distorted. You cannot really trust the shape of those contour lines, right? The reason is because if you look at the interval of the horizontal and the vertical axis, they are different. So on the horizontal axis, 50 units is this long, right? But on the vertical axis, the 50 units is only this long. Do you see the problem now? Right? That's not exactly the same the thing that we want to sort of see. So how do we actually correct this kind of default behavior? We can use the axis equal. So if you type axis equal, then the horizontal and the vertical axis are going to will have the same kind of interval. Let's select this portion and evaluate the selection. Let's rerun that. So now you can sort of see that. So now 50 units. Let me still put it back into the. Now 50 units on the horizontal axis is this long, right? And then 50 units on the vertical axis is the same length, right? So you can sort of see that. Our correct solution is supposed to be 19 dogs, which is probably here, right? And then 29 chickens, which is probably over here, right? So it's The optimal solution, the correct solution, is actually located at a region inside of the contour that's actually has the smallest value, right? Has the coldest color, right? Coldest color means the smallest value of ERL2, right? That's how we actually computed the difference, how we actually quantified the difference between the predicted y and the actual y, right? So now let's this is just the contour, right? This is just the contour plot that shows you how this kind of a difference between the predicted and the actual y is going to vary on this two-dimensional dog-chicken plane, right? The horizontal axis is the number of dogs, and then the vertical axis is the number of chickens. And depending upon the number of dogs and the number of chickens you actually have, you're going to have the number of dogs and number of chickens you're going to assume, then it's going to give you different differences, right? Different difference between the prediction and the between the prediction and the actual calculation, actual results, right? So now on this two-dimensional plot, let's try to actually take a look at how x actually evolves throughout this kind of iteration, right? And in order to do that, we need to actually store the x values that's actually used for every iteration, right? Let's store it into a vector let's call it xx, right? Zeros, it's gonna be 2 rows, right? No, not exact 2 rows, but the length of x, this many rows, and ni, this many iterations, and this many columns, right? So every column is going to be the x value for each of the iteration, right? And then because x has an assumed starting value, right, we need to actually add one more to it, right? And then the first xx, the first column of xx, the first column is going to equal to x. That's 150, 150. Right? And then after we have made any kind of changes to x, we store the changed x value into xx. So xx II plus 1 is going to equal to x. Why do I want to do a plus 1, right? Because the first column of xx has been used to store the starting value, right? So every time you make a change, so for the first iteration, you want to actually store the changed x into the second column of xx, right? So it's 1 plus 1, that's 2, right? So that's why you need to add 1 to it, right? And then once we have this xx vector that actually tracks the position of x for every iteration, we can actually try to plot the xx vector onto this two-dimensional contour plot, right? So in order to actually plot both the curve and also the contour, we need to hold on, right? Hold on means that after the contour plot is finished, is completed, when I actually plot the xx value, the first row, the first row, right, and then the second row, I want to plot this curve on top of the contour. I don't want to erase the contour. If you don't write hold on here, then it's going to erase the contour plot, right, and just plot the curve. So here, the horizontal axis, that's the number of dogs throughout my trajectory, throughout all the iteration, and then that's going to be the number of chickens throughout the iteration, right? And then I'm going to specify the color as a magenta lines, and then with a line width. So everything that's inside of this single quote is a string, and this kind of string actually is some kind of option to the plot function. So line width is going to be 2. Let's give a line width of 2, right? And now let's just rerun this piece of code. So we need to rerun this particular cell in order to actually create the xx. Hold down the Control key, press Enter, and now it's finished running, right? And then let's close this particular figure first, and then let's rerun this figure. Let me just select this section and then evaluate the selection. It doesn't look right. We started with 150, and then stopped at where? Let me take a look at the size of XX. Let me look at the last column of XX. Looks like it's right. But why it's not plotting? Why it's not plotting right? Let me look at the first column, 150, right? That's supposed to be here, right? So it looks like the starting point is right, but the ending point is not. The ending point is supposed to be 1929, but for some reason it's not displaying 1929. Let me see. The first row, right? And then the second row. I was using magenta. And then maybe if I do not use line width, let's see if it's gonna work. But maybe change to a different color, say okay. It looks like there's some problems with the display. So let me hold off. And then let me just plot the line. Oh, I'm really sorry. I got the index mixed up. Right, it's not the first column. It's actually the first row, right? So the first index is actually for selecting the rows, and then the second index is for selecting the columns. So if I want the first row in all the columns, what I should have done is to put one here and a column here. So that was one of the mistakes that I just made, I guess. Right. So it's the first row. It's not the second. It's not the first column. Second row. Right. And then let me try to rerun it. Yeah, now it looks like it's correct, right? So it started at 150 and 150. And then what it actually does is that it's gonna go along this particular direction for a really long time. Right? But if you actually pay attention to the contour lines and also the trajectory that our iteration is actually following, you can sort of see that this trajectory is almost perpendicular. It's pretty much actually perpendicular to all the contour lines, right? And it's actually moving from regions with warm color to regions with cold color, right? It's actually following this kind of trajectory, which is actually perpendicular to the contour lines, and goes from regions with high error, very large errors, to regions of smaller errors. And then once it actually reached this particular point, right, it actually made a turn, made an almost a 90-degree turn, right? It's a kind of very sharp turn, and nobody's actually telling the computer to actually, nobody is actually telling the program to actually make this turn. It actually made this turn automatically. See, it's actually making this kind of almost 90-degree turn automatically, and then again follow this trajectory, reaching the optimal value, to the correct value, to the correct solution, right? And again, if you look at this particular trajectory, and if you actually make more contours, if you plot more contours, you will see that this trajectory is again perpendicular to almost all the contours, right? If you actually plot the contours. For now, in this particular direction, the number of contours is kind of sparse, right? But if you plot more contours, you will see that this line is actually perpendicular to those contours, right? So that's one of the kind of behavior of the so-called steepest descent. It allows you to actually follow the direction that's kind of perpendicular to the contour lines, and then it's going to descend. That's why it's called descent, right? It's going to go from regions with high value to regions of smaller value, and during its descent, it's always going to follow a path that's going to be perpendicular to the contour lines, right? And if you want to explore more, my graphics is kind of slow, but if you want to explore more, you can sort of blow up. You can blow up the regions where it's actually made the turn, right? And then if you want to sort of plot more contours, you're going to see that while it's actually following this particular turn, it's actually also perpendicular to all the contours it's actually passing through, right? All the contours it's passing through, it's going to follow that direction that's perpendicular to contours. Next time, in the next video, we'll try to actually encapsulate this steepest descent, this particular loop, into a function and then apply it to multiple kinds of problems that's going to require a solution of linear systems. We'll see that we can actually use the same code to solve for the decoding problem, right? When we did the matrix multiplication, when we wrote this particular function, we applied this function to the matrix encoding problem, right? Which is just the matrix multiplication. But now let's see if we can actually apply this inverse function to matrix decoding problem. And then let's look at another example that's going to involve the solution of a finite difference problem.